Good evening, dear all. Let us define electric flux. And using the formula of electric flux, let us formulate the Gauss's law and some few points to be remembered for the Gauss's law. Okay. So now we begin with what is electric flux. Electric flux, as you can see in the diagram, is the number of electric field lines that are passing through the given surface whose area is delta S. Now, very important is the angle at which we are holding the surface with respect to the electric field. So now here you can see a surface which is perpendicular to the electric field. So we have the electric field lines in this direction as I am showing, and we have placed the area, surface area, part of the surface which we are considering perpendicular to the electric field. Fine? Okay, now what should be the direction of the area element? We can, instead of saying it as a complete area, we are selecting one part of the surface area, so we call it as the area element. So what should we consider the direction of the area element? Remember this very carefully, because there the confusion comes. We have placed the area element perpendicular to the direction of the electric field. What is the direction of the area element? It is always perpendicular to the surface which we are considering. So that here you can see electric field direction and the direction of the area element is same. Therefore, if I consider the angle between E and delta S, theta is equal to 0. We'll come to the formulation part, but first understand how to find out the angle between the electric field and the area element into consideration. Here, how have we placed the surface element perpendicular to the direction of the electric field, but how do we take the direction of the area element, which is always perpendicular to the surface which we consider. So the direction of the area element is same as the direction of the electric field in this case. Okay, now let us go to this case. In this, the area element is kept a little bit slant compared to the direction of the electric field. So what should be the direction of the area element? Perpendicular to the surface in this way. So I just place it here. You can see this is the area element which we have considered in the electric field. And what is the direction? The direction is perpendicular to the area element. The direction of delta S is perpendicular to the area element. So you can see this is the surface and the direction of the area element is delta S. And this is the direction of the electric field. So what should I say? The area element has this direction, delta S, and what is the direction of the electric field as seen? E. Now both are vectors because we are talking about direction. Electric field is also a vector and area element is also a vector. Okay, so what is theta here? Something like theta dash or theta 1 we can consider. Now coming back to the definition, we can say they are the number of electric field lines passing through an area. This is just like simple example. You are sitting in a flowing water with a surface. How much water is flowing through this surface? That is the flux. That is the electric flux. That is the water flux. Because we are considering electric field is flowing, this example can be considered similar to that of the electric flux. Fine. So the angle has to be determined between the direction of the electric field and the direction of the area element. What is area element? A part of the area which we are considering. Now, if at all there is some confusion, let us consider one flat surface as an example. Now, here I have taken one simple notebook and considering this surface as the area element. Now, in the very first case, I have placed the surface perpendicular to the direction of the electric field. So, how have I placed it? This surface which I am considering is placed perpendicular to the board. That is the direction of the electric field. So, what is the area element? Area element is perpendicular to this surface. So, what is the end result? The direction of the electric field is also in that direction. The direction of the area element is also perpendicular to the surface. So, in that direction, so what is the angle between E and delta S? 0. Right? Okay. Similarly, in this case, what have I done? The same surface I have tilted and placed here. This is the surface. Okay. So, if I have tilted it, then what is the direction of the area element? This way. Right? Okay. And what is the direction of the electric field? Along the board. So, what is the angle? Some angle theta is equal to 30, 45, 50, whatever. Now, suppose I place this area element or the areas, the surface which I am considering just on the board. Then what is the direction of the area element? Perpendicular to the board. And what is the direction of the electric field? Along the board. So what is the angle between electric field and the area element? 90 degrees. How? This is the direction of delta S. This is the direction of electric field. So the angle between E and delta S, in that case, if I place this surface flat, will be theta is equal to 0 degree. Sorry, 90 degree. Right? Okay. So here we have to be very careful what is written in the question and determine the direction of the area element. Direction of the electric field is already given to you. The direction of area element is always perpendicular to the surface which we are considering. So if this is the surface, then this is the direction of the area element. If I keep it like this, area element goes like this direction. If I keep it like this, then the area element goes perpendicular to it. If I keep it like this, then the area element goes perpendicular to it. So every angle I turn the surface, its area element will be exactly perpendicular to that surface. However, I tilt the surface element. Fine? Okay. So now we formulate the formula, or we write the formula of the electric flux for this area element as delta phi, which is the flux for only this much portion delta S, is equal to E, which is a vector, dot, it is a scalar product, that's why I have written dot, delta S arrow. Okay, where E vector is the electric field which we have considered and delta S arrow is the area element which we have considered for the whole portion of the surface. Fine. So as we know from our 11th standard, how do we consider a scalar product or a dot product? We can write A dot B is equal to AB cos theta, where theta is the angle between A and B. Similarly, here I can write delta phi is equal to the scalar product of delta phi is a scalar. Scalar product of E dot delta S, both vectors. So I can write E delta S cos phi. Sorry, cos theta. Where theta is the angle between E vector and delta S vector. Fine. Okay. So remember this formula as the scalar product, or remember this formula as the scalar product of E vector and delta S. Okay. Now coming back to the angle, what is the angle in this case? Theta is equal to 0. So if I write theta is equal to 0, then in this case what should I write? Delta phi? Delta phi is equal to E delta S cos 0. Cos 0 is 1. So for this particular situation, I get maximum flux. Okay, that's why I can write it as max. So when do I get maximum flux passing through an area? Only if the angle between E and delta S is 0. Remember. Okay, now in this case, what do I write? Delta phi is equal to E delta S cos E delta S cos phi dash. Phi dash can be theta phi dash can be 30, 60, whatever. Okay, then here in this case, I can write delta phi is equal to E delta S cos 90. What is cos 90? 0. So what is my answer? 0. So in this situation of theta is equal to 90, I get flux 0. What is the meaning? It can be asked the other way around also. When do I get a 0 flux? Only if I keep the surface which I am considering in the same plane as that of the electric field. Then I will not have any lines passing, electric field lines passing through this surface. So flux is 0. If I keep it like this, maximum number of lines are passing, as I said, just like flowing water. Maximum amount of water will be flowing through the surface. So I will get delta phi max because theta is 90 between E and delta S. If I keep it somewhere slanting, then lesser number of electric field lines will pass through this surface compared to this. So I will get an answer lesser than this because cos takes a value between 1 and minus 1 as we all know. Fine? Okay. So these three formulas or values also keep it somewhere in mind. It can be turned and asked when is the flux maximum? If theta is equal to 0. When is the flux 0? If theta is equal to 90. Fine. The other formula is ready with you. Whatever theta is there, substitute. Fine. So this formula has to be remembered so that we can derive the Gauss's law using this formula for flux. Fine. Okay. So take a screenshot of this also. Now using the definition of the electric flux, we shall derive or formulate the Gauss's law. Fine. Okay. Now here, as you can see, I have considered one spherical surface. This is a spherical surface which I have considered and I have named it as S. Out of that spherical surface, I have considered one cone portion of the surface delta S. Okay. And the radius of the sphere I have considered as R. So I have considered a sphere, naming it as S with the radius R, and within this surface I have considered an area element denoted by delta S. Fine, placed at the center of the sphere. Now within this sphere, let me consider a charge Q placed at the center of the sphere. Fine. Okay. Now, as per the rule of the direction of the electric field due to the charge anywhere, if it is positive, I have to show the direction of the electric field radially outwards from the charge. So, I can show it radially outwards from the charge. So, this is the direction of the electric field due to the charge Q placed at the center of the sphere. Okay. Now, similarly, for an area element as discussed just now, I consider this portion direction as radially perpendicular to the surface which is available to me. So, I have to consider the direction perpendicular to the surface which I have considered for delta S. So, delta S direction is also same as that of E. Right? So, what is the angle between E and delta S? If the directions are same, then theta is equal to 0. Fine. So, I am ready with the diagram. See, drawing of diagram is the first important part of any physics derivation or a numerical. If your diagram is correct, then the examiner understands, yes, you know what you are doing. And then you describe whatever you have made, like you have taken S as the surface area, which is 4 pi r square, as can be seen. You can also write delta S as one of the area element or surface element. Fine. Where r is the radius of the sphere. Okay. These are the Q is the charge placed, where I have placed it at the center. So this description you have to write once you draw the diagram. That is the second thing you have to do in any derivation. Okay. Now we use the definition or the formula of flux, electric flux, for this portion of the area element which is of the shape of a cone. Fine. So I will have delta phi is equal to E arrow dot delta S arrow. If I use the scalar product of these two vectors, I will write E delta S cos theta. My theta is 0, so delta phi is equal to E delta S. This is what I get. Now, in the previous section, using the Coulomb's law, we have the formula of the electric field due to the charge Q given as E is equal to KQ upon R square. Fine. Then I can even write K as 1 upon 4 pi epsilon naught. Fine. Okay. So Q upon R square. If I write its vector notation, then I can write a arrow here and I can put an r cap here, where r cap is the direction of the unit vector r. Fine. So now in the formula of delta phi, I substitute the value of E, scalar part of it, which can be written as 4 pi 1 upon 4 pi epsilon naught Q upon R square. This portion is the E, which I wrote just now, multiplied by delta S. Now, this flux, electric flux, is for only the portion which we have considered as delta S. I want the electric flux for the whole surface S. So what do? I can just integrate for the whole surface. This is a symbol of addition or integration for the complete surface, and because all this portion which we can see here, Qi is fixed, R is fixed according to the surface, which can be considered as constant, I will only take integration for the whole surface of the delta S part. Fine? Okay. So now if I take the integration of every such area element, I will get the total flux phi is equal to shuffling the space or the place of R square with epsilon naught. I rewrote it, only shuffled these two places so that it is convenient for me to later on cancel it. Now integral of delta S is a summation of all the cones of delta S, delta S, delta S. So what it will be? It will be the surface area of the sphere. What is surface area of the sphere? 4 pi r square. Am I right? Where I have considered the surface area of the sphere as S is equal to 4 pi r square. Fine? Which I have substituted here. So now here it is seen clearly, this portion and this portion I can cancel. So what do I have? I have phi is equal to Q upon epsilon naught. Fine? This is another formula according to the Gauss's law for the flux passing through a surface, where we have to only consider the charge enclosed by the surface. Q is the charge enclosed by this surface. So flux phi is equal to Q upon epsilon naught. Now let us define the law. So what is the definition of the law now? What can I say? I can say that the law states that the flux is the is 1 upon epsilon naught times the charge enclosed by the surface into consideration. This is the Gauss's law which we have done. Okay, so I just bring this down again. Fine. So this is the Gauss's law where it states that the flux is 1 upon epsilon times the charge. You can even say net charge enclosed by the given surface. So here comes one more question. Suppose I have one more charge here. Say I have one more charge here of same magnitude. I have another one here, Q1, of this another magnitude. Should I consider this two charges addition here in our formula? No. I should only consider the charge which is in the surface of consideration. Okay. So let us understand this with few more examples. First, I shall move and you can take a pic of what I have taught you. Then I shall move to variations in the consideration of the net charge when you are considering the Gauss's law. In Gauss's law, you are considering one imaginary surface around the charge, which is called as Gaussian surface. This is called as what? This is called as Gaussian surface. Which has no role to play in the formula which we have written for the flux. It can be of any shape because it is not there in our. Fine. So the surface which we are considering around the charge is called as the Gaussian surface. Fine. I shall move and you can take a pic and then we will go to the variations in Gaussian surface. Fine. Okay. Okay. As discussed earlier, what should be the shape of the Gaussian surface? It is not there in our formula. What is our formula? Phi is equal to Q upon epsilon naught. So the shape can be anything. The shape can be a proper circle also. Fine. Then the shape can be a cuboid also. Fine. Okay. So here I have considered one irregular surface. I have considered a circular surface. Here I have considered a cuboidal surface. You can even consider it as a cube. Right? Okay. So now here in this case, suppose I have a charge Q1, Q2, and here I have a charge Q3. Let me have one negative charge also, 2Q. Then what is my answer for the flux? Should I consider this? No. Should I consider all these charges? Yes. What is it? Phi is equal to Q1 plus Q2 minus 2Q upon epsilon naught. Fine. Okay. Now in this case, I can consider some charge Q plus 2Q minus 3Q. Here there is one phi Q. Should I consider this 5q or negative 4q in my formula? No. Only I have to consider the net charge as the charges within the Gaussian surface. So what is my formula here? What is my answer here for the flux? Phi is equal to q plus 2q negative 3q upon epsilon naught. So it can be 0. Right? Now here let me consider one combination of q and 2q also is available within the surface of the cube. So what is my answer here? Phi is equal to 2q plus q divided by epsilon naught. Now because in a cube all the surfaces are equal area wise, if they are asking us what is the flux through one surface, then what should we do? Let we consider the n surfaces, then our answer will be phi 1 through one surface. One of the surface is equal to 3q, 2q plus q, 3q upon epsilon naught divided by n. In simple words, phi upon n. Okay, phi upon n. That is the flux through one of the surface, any one of the surface. So now let us consider two concentric surface areas. Say this is S1, this is S2. We have already found out the flux of the surface S1. We'll name it as phi 1. We have seen the answer is 0. Phi 1 is equal to 0. Now what should I do when I am asked about the flux through S2? Should I consider this charge? No. Should I consider this charge? Yes. So what is my phi 2 for S2? It will be 0 as written here, q plus 2q minus 3q becomes 0 and negative 4q divided by epsilon naught. So what is my final answer for phi 2 for the surface area S2? Negative 4q divided by epsilon naught. So in this way, for different types of surfaces, the value of flux will depend upon the charges enclosed in the given area, whether it is an irregular surface, whether it is a circle, whether it is a cube. If they are asking the flux through total cube, then this is the answer. If they are asking flux through one of the surface, then phi for the whole cube divided by n. If flux through a single surface is asked for such regular figure like a cube, then we have to calculate the flux through the whole cube and divide it by n. That is the number of surfaces for the cube. Number of surface for the cube is 6. So we can write phi upon 6. That is the flux through one of the surface. Right? Okay. Now I take or I move from here and you take the screenshot of whatever is done or understood by